short session, by the way. So first, let me introduce Bence Signeri. Bence is from the Faculty of Electrical Engineering and Informatics, and they have a common project with civil engineers. So he will show us nice digital twin applications. After his presentation, let's have some questions, discussions about that, and then we will have the panel discussion before the lunch, and after the lunch we will have the graduation ceremony. So that's all for today. So Bence, the floor is yours. Pardon me? Oh, no, after the graduation ceremony, you are also welcome from a cocktail. Oh yeah, cocktail party. Yeah, sorry.
Thank you. Good morning. Welcome. My name is Bence Signeri, and I want to introduce our team. So, Kővári Bence is my supervisor. I am a PhD student at the Department of Automation and Applied Informatics. I graduated as an IT engineer, and we are developing software, and we are in a cooperation with the civil engineers Jó Attila, Völgy István, Kollár Dénes, and Kenéz Ágnes. What I will talk about is bridges, digital twins, machine learning, and so on. But why I am here is that there will be an important role in my presentation about artificial intelligence. So I want to introduce some basic definitions. These are buzzwords that are commonly used nowadays, but sometimes they are misunderstood. So, for example, ChatGPT is used nowadays everywhere, and it is called basically artificial intelligence. But in fact, artificial intelligence has a different definition in IT, if it has any good definition. So these are commonly used words nowadays. I want to make more clear it. So the greatest set of artificial intelligence algorithms is what we call artificial intelligence in IT. For example, in the 1970s, if they developed a robot playing chess, it was already some kind of artificial intelligence. So it is an artificial intelligence system. Then in the 80s, 90s, some machine learning approaches appeared. For example, support vector machines, k-nearest neighbor, and so on. So these systems. What is an important difference between artificial intelligence and machine learning is that machine learning is learning from data. So it has a training data set, and the artificial intelligence learns based on data. So in fact, it is trying to learn some pattern matching. So it is trying to learn patterns, what we cannot see by human eyes. But in the case of an artificial intelligence system, there is no need for a training data set as a requirement. And finally, we have deep learning methods. These deep learning methods are some kind of machine learning algorithms. Deep learning methods are most commonly used nowadays. So if there is a grand breakthrough, then those are achieved by deep learning frequently. For example, those methods are used in image processing, audio processing, for example, in ChatGPT, and so on. I want to make a bit more clear in an example. For example, chess playing robot is an artificial intelligence system. In this case, we do not have to get training data. We do not have to get training data, so it's not a requirement. It wouldn't be good if the chess playing robot would just learn patterns. It has to learn some thinking, which is based, and it is based on preliminary defined statements or actions. So we know how these puppets can move, and based on these steps, we can simulate a game. And in fact, we want to train the chess robot to play it as well as we can. And in this case, the AI is not it is not sure if it is learning, so we can have preliminary defined rules, for example. Those were invented in the 70s, but maybe it can also be trained by reinforcement learning, where the chess player, the chess robot, learns from the games it has already seen. But that kind of game will be a machine learning because it learns from data. What is a machine learning task? For example, face detection. What is the main difference between playing chess and face detection? The main difference is that I can explain in chess playing that why I did that action, or for example, I can also easily understand the state of the chess. But for example, if I ask you how to detect a face, then it's a more complicated question. So you can say that, for example, a face has eyes and a mouth, nose, and so on. But then I will ask, okay, but how to detect an eye or a nose and a mouth and so on. So in this way, we are at the same position. For these kind of tasks, machine learning algorithms are commonly used, where we have a training data set that contains faces, and we want to detect faces on them. And how this process goes. So in the case of deep learning, you can see that, for example, we have a training data set, and on this training data set, we want to detect the faces. And the first thing is that we need is a labeled data set. So here you can see that we have the raw data, but also we have a labeled data set. The labeling here means, for example, red bounded rectangle, so it can be defined by 4 numbers, and the machine learning algorithm should do or the deep learning algorithm should do the following. It should calculate these 4 numbers based on the input, which is an image. So this is the deep learning basically. Why is it not easy task? Because it has to also work on unseen images. So if we just want to train on them, then we can memorize everything. What is more interesting, what happens if we have unseen images, and the system should work also on this kind of data. And how can we find this function, this F function? So how can we map the inputs to outputs? For example, in this case, you can see the input on the x-axis and the output on the y-axis. And the red points show the training data, and the blue ones are the test data that we do not train on. And you can see that, for example, a linear regression can be a good model, but it will have a higher error. And for deep learning, it is an important feature that neural networks are universal approximators. It means that, in fact, it is mathematically proved that a neural network can fit to any kind of data set. So it can happen that this green light will fit on all red points with a small error, and it is proven. But it is called the no free lunch theorem, that, for example, in this case, this fitting is not so good, because you can see that the blue points are are far from this green line when compared to this case. This case would be a robust solution. In fact, this is the main task when developing neural networks, to have also a validation set, and the solution should work well on the validation set and then on the test set, not just on the training data. And not so in the case of neural networks and deep learning systems, it is also an important question, what is the architecture of it and so on, but it is the basic task. Now I will start to speak about my topics. So our research group developed the bridge weigh-in-motion system. First, what is a weigh-in-motion system? It can estimate axle loads without the need for stopping with vehicles. It can be really practical because in this case, all vehicles crossing the road can be measured without stopping them, because if we want to stop a vehicle then and we want to measure the axle loads, then it can take 2 or 3 minutes, and in this case we can only measure 30 vehicles in an hour. But using this system we can measure the axle loads for all of the vehicles. And axle load estimation is a really important task when maintaining road infrastructure, and because if we do not have we do not enforce regulations, then we will have potholes, and also the braking distance will increase. It is also a safety problem. That's why we need the weigh-in-motion systems. The most commonly used weigh-in-motion systems are the pavement weigh-in-motion systems. So weigh-in-motion with pavement, so when the sensors are embedded in the asphalt pavement, in those cases we can measure the axle loads. What our research group has developed is a bridge weigh-in-motion system. It is a bit different because in this case the bridge is used as a scale. So the bridge is used as a scale, and by measuring the strains and so accelerations on the bridge, we want to estimate the axle loads. What are the main use cases and advantages, disadvantages of a bridge weigh-in-motion system? For example, sensors are placed under the bridge deck. So we commonly use strain gauge sensors, but also acceleration sensors can be used. And these sensors can be installed easily because we do not have to disturb the traffic. And also these sensors are really cheap when compared to asphalt embedded in the sensors. And it can be said that, okay, but it is a disadvantage of these bridge weigh-in-motion systems that they can be installed only on bridges. But it is an important thing that, for example, in Hungary or in every country there are big rivers, and if someone wants to cross the river, then they have to go across that bridge. So these bridges are strategic points, and in this way they can be commonly used. I have already told you that it is a non-invasive solution. So sensors are placed under the bridge deck, and it does not need any disturb of the traffic. We do not have to do anything with the asphalt as well. So that's why it is a non-invasive solution. The installation costs are lower when compared to pavement weigh-in-motion solutions because the sensors are cheaper, and also the installation is cheaper. Repair and maintenance is also easier because if one sensor goes wrong, then we just have to go under the bridge and repair that sensor. And finally, why these bridge vehicle motion systems are not widely spread, because the accuracy needs to be further refined. So our goal was to refine the accuracy and the precision of that system. We have a prototype on the monostory bridge in Komárom. It is a bridge over the Danube River, and we have straying oaks installed in that cross section. And our first goal is to create a bridge vehicle motion system that can estimate the axle loads of the crossing vehicles, is the short-term goal. But in the long term, the goal is creating a structural health monitoring and real-time digital twin system where the monitoring data of bridge vehicle motion system data can be used. So we want to create a digital twin system, not only a structural health monitoring system. Structural health monitoring systems in bridges have really wide literature. What we want to do is a digital twin based on the vehicle motion data. So in the case of a structural health monitoring, we have the monitoring, so we have straying oaks, temperature sensors, and so on. And we have measurements at some given points. But using the signal measured and using the finite element method model of the digital twin system, we want to create a real-time structural twin for the system, so that we can measure or simulate the structural data for every point on the bridge structure. And here comes the bridge vehicle motion system, because if we have the vehicle data, then we can simulate everything on the finite element method. And in this case, we can update the finite element model based on what we have already calculated. It is also a good thing that, for example, in this case, if we have axle load data in the short term, then these systems can be solved more easily, because in this way the system has a short-term advantage next to the long-term advantage of a real-time digital twin. Here you can see some detailed plans, so how sensors are installed on the bridge. You can see that here is the Komárom Monastery Bridge, and 10 sensors are placed in that cross-section, and 16 sensors are placed in that cross-section. It is called the main sensor array, where the 16 are placed. The secondary sensor array is only needed because we want to estimate speed, vehicle speed. It is needed for our system. That's why a lower amount of sensor is enough in that case. And also you can see how those sensors are placed under the bridge deck. Here you can see visualization of the data. For example, in the case of the monostory bridge, we have 2 lanes, and for these 2 lanes, the sum of strain signals are visualized. So for example, you can see here that we have a vehicle crossing the bridge, and what can be seen easily is that, for example, the axle positions can be detected easily by local peak extraction in these cases, but also we can see what are the what we struggle with. So the first thing is that if one vehicle crosses the bridge in one lane, then it has also some effect in the other lane. And the second thing is that so the second is the dynamic effects. Most works refer to this as some kind of noise, but this is the effect of dynamic effects. I have already mentioned that this project is in a cooperation where software engineers and civil engineers cooperate. Our software team develops the artificial intelligence for this case and also the software, while the civil engineering team does the structural analysis, the monitoring, and the digital twin calculations. Here you can see how a typical bridgeway in motion pipeline looks like. So we have a database of strange signals. It is streamed in real time. Then the first step is the vehicle window detection. What is the vehicle window? The vehicle window is the time interval when a vehicle was crossing the bridge in the relevant cross-section, so in the cross-section of the main sensor arrays. Then the next step is the speed estimation. It can be done because we have sensors installed in two cross sections, and inductive loop can be used in this way, similar algorithm to that. And the next step is axle detection. In the case of axle detection, we want to detect those timestamps when an axle was crossing the bridge. And if we know the axle timestamps and also know the speeds, then we can calculate the axle spacings and also the trajectory of the vehicle on the bridge. Also in high-speed vary motion systems, we can assume that the speed of the vehicle is near constant. So in this way, the vehicle trajectory can be calculated. And finally, the axle loads can be calculated based on this trajectory. How this calculation works in general. So the most basic implementation of this, so the most basic method is the Moses algorithm that builds on the definition of influence surfaces of bridges. So if we know all the vehicle parameters and also we know the influence surface of the bridge, then using a simulation, we can simulate what kind of signal should be measured on the bridge. And in the case of the artificial intelligence, we already know the speed, the axle spacing, transverse position, and so on. But we need the axle loads, and we want to find the axle loads so that if we simulate with those axle loads, then the measured signal and the simulated signal will be as close to each other as it can be optimized, and those axle loads will be used. What are the main challenges where this Moses algorithm needs some refinement or it cannot be used? So this Moses algorithm is basically used for axle load estimation. So it is not used for speed estimation or for axle detection. The main challenges are, for example, when there is traffic in more lanes. If there is only one lane, then it is an easier task. So bridgeway in motion systems for one lane railway bridges are developed frequently. So those were already known in the 90s or at the beginning of this century. But if there are more lanes, then it is still a complex task. How can we handle more lanes? The next is, what should we do with tandem or tridem axles? For example, what is a tandem and tridem axle? So there are closely spaced axles. In those cases, axle spacings are lower than this distance. And in those cases, you can see that in the strain signal, the axles cannot be detected as clear local peaks. It is a problem because the local peak algorithm then cannot find the axles easily. And that's a commonly mentioned problem in those cases. Also, it can be also represented by an axle group simply, but it is better if we know that this axle group is made of 3 axles. And that's where we use the, for example, deep learning or artificial intelligence, that we wanted to detect the axles based on deep learning. And how can it be done? Deep learning needs training data, as I already mentioned, and that's where we need a labeled data set. And how can we label a data set? One scenario is manual labeling. It can be really resource intensive, time consuming, and so on. It can be also a solution that we can detect objects based on a camera, but then we will have the error of the object detection system in the workflow, and also regular cameras have a lower FPS compared to these strain measurement systems. And also, for example, in the case of axle load estimations, the axle loads can be estimated when vehicles are stopped. So these are the main scenarios, but we used another one. We created a synthetic data set. It means that we created a data set where we define the vehicle parameter, speed, axle spacing, axle transfer position, and so on. And using the finite element model of the bridge, we simulated a larger synthetic or simulated data set. It contains also the signals, and also we have the labelings because we calculated everything from them. And in this way, we simulated more than 100,000 scenarios. It also includes multi-lane traffic and also contains complex vehicles, so the maximum number of axles are 9, which is not so real-life scenario, but if the system will work on those scenarios, then it will work also in real life. That was the case. And I can also mention that, for example, if we want to have multi-lane traffic label data, it is also a very hard task because it is not so frequent as it is assumed. And for example, in the case of axle detection, here is a small slide how we used AI. So I want to mention how face detection worked. We have images, we have the labels, these red rectangles, and we want to train the AI for these image bounding boxes pairs. How does it work in the case of this bridge vehicle motion system? The input is the strain signal, so you can see that we have the strain signal, and the output is a vector or a sequence where there are zeros on those time terms where the axle was not crossing the bridge, and ones, or these red things, where there is when an axle was crossing the bridge. And in fact, in this way, we train the deep learning, so the neural network, on this measured signal and these vector pairs, and the AI learns it and learns how to detect axles. And in this way, we can also detect the single axles in an axle group, and it will lead to more accurate axle group load estimation. Here you can see some results that has been achieved on the monostory bridge in Komárom. You can see that according to most features, so gross vehicle weight, which is the total of some weights, axle group weights, heaviest axle weight. We achieved the coast 323 classification A. It is the best class. It means that, for example, the gross vehicle weight can be estimated by at most 5% of errors in 95% of cases. And also it's an important thing that it is only true for vehicles that are above 3 tons, so not for low-loaded vehicles, but those are not so interesting in those cases. And I also want to show some further AI usage. For example, one case is when sensors have a failure. So for example, we have the sensors, but one is failing. And what happens in those cases? The best scenario if we can repair it at once, but it can happen that it takes some days or weeks to arrive there. And if it does not work, then the AI system will provide non-accurate data. And I developed the deep learning or a linear regression based system or machine learning based system where the signal of this sensor is calculated based on the signal of the other sensors. And for example, in this case, if the blue is the measured without the outage, then it can be calculated by AI, and the system will not be as precise as with it, but using this algorithm, the system will still work with a B or B plus class. And what I am working on nowadays is that we have a working prototype for orthotropic steel bridges. So we can generalize it for other orthotropic steel bridges as well. But we want to generalize this method for reinforced concrete bridges. One of the main challenges in these cases can be seen here. So on an orthotropic steel bridge, you can see that due to the influence line shape, the axles can be detected easily by, for example, local peak extraction method. But for a reinforced concrete bridge, it's not so easy. So for example, with human eye, it is hard to see where are the axles. If someone watches them a lot, then they will learn, but it is not easy. And what can we do in those cases? And that's where machine vision can come. So if we also have a camera installed, which is also a requirement, for example, for license plate recognition, then we can detect the axles based on this axle detection system, based on the camera, and the whole trajectory of the vehicle in this phase can be calculated, and based on this trajectory, the axle loads can be calculated. And also there are other challenges here, for example, synchronization and so on. I am working on this thing at the present, and so how machine vision can be used in these scenarios. It would also solve the case when it is not a high-speed variant motion system, and for example, the vehicle speed varies. And finally, you can see that those modules are already implemented in our case. What we need is it is in Hungarian, so the update of the finite element model is needed. Thank you for your attention, and if you have any question, I will answer them.
Thank you very much, Bence. And now this is time for questions from the audience. Yes, Mathieu, you can't wait to ask.
Hello, good morning. Thank you, Mathieu, for your presentation. I'm a civil engineer and working on bridges, so I'm quite interested by this topic. Just to understand the context, what is your main goal for the bridge weight in motion? What do you want to achieve in the end? If you have access in the end to the load axle, but in the end, what do you do with? Is it like for control of something? What do you want to? What is your purpose at the end when you have all the data? And you know the weight of the.
What is the usage of axle loads?
Yeah. What do you do with that in the end?
Our main short goal term is to enforce regulation.
Yeah.
So it is the most useful, for example, for the public roads and for the infrastructure maintenance. And if we want to also create a digital twin, so there is the short-term goal is this bridge weight in motion system that can be used for regulation enforcement, but for the long-term goal, we want to create a real-time digital twin where bridge maintenance actions can be prioritized based on the calculated data. And that's the long-term goal, but in the short term, the requirement is more than the axle loads because we have requirement for
you do have the same everywhere, I think, because we have a lot of problem in France with huge trucks crossing bridge, but and they are much heavier than the regulation, and we have issued, and one bridge collapsed in France because of that. A truck of 50 tons crossed a bridge limited to 10 tons, so 50 tons out of 10 tons, of course. Yes. But the thing is, we need to control the weight of the truck before entering the bridge, not when they are already in the bridge, because it's too late.
Yeah, there are two gaps in this case, I think, because the one is that we want to enforce that we want to control that there are no trucks over 40 tons, for example, but in the other way, from the view of the state, they want to make these trucks pay the fees. Yeah. And that's also a very important thing because now there is a lack of infrastructure for this. Yeah, there is an infrastructure for this in Hungary, but it could be it has lower costs, and also it can be made more widespread if it can be also generalized for reinforced concrete bridges.
Another point, but the use of your work also, and especially for orthotropic steel deck on the stiffeners. Do you use your results to calculate fatigue resistance? Because you have access to all the data of the strength, and you can.
So since I am an IT engineer, I work mainly
in
a data-centric way.
Not for the civil part, the civil engineering part.
Yes, civil engineering, but we also have the measurement part, so Völgyi István.
Because I know, like, specifically exactly where you put your sensors on here.
Oh, have we
on the stiffness? No, when you have your chart before. Yeah, here.
So have
this point exactly here when you put your sensors. Here we have a fatigue. We can have local fatigue issue, and it could be very useful to also use your data to control fatigue cycles.
Yes, it can be also used for those as a fatigue data.
And if I understood correctly, you put the sensor exactly on the pylon because it's a rigid part, and you wanted only the local deformation. You didn't want to put this. Normally, when we want to do SHM on a long bridge like that, and you want to match your measured data with finite element models, we put sensor also in the mid span, where it's very soft. To be able to match with eigenmodes and eigenvalues, but you are not interested in that.
In this case, this sensor location was because we had constraints, so we couldn't locate sensors here because of the electricity.
Because you had to put a long wire to plug. You needed electricity.
Yes. So the electricity was in the pylon. And that was a really hard constraint for us to place the sensors near the pylon.
For the local deformation and transversal, it's quite smart actually, because you have only access to the local deformation of the tires and the axle, and you don't need the global deformation of the bridge.
We do not need the global.
Yeah, but if you want to do a global SHM model, it could be nice to also have the mid-span deformation.
Yes, but that's so if we know the axle loads of the vehicles, then we can also simulate that if the vehicle was crossing here at a given timestamp with a known vehicle speed, then we can also simulate when it was crossing here. And in this case, we can update the finite element model based on this information.
But how long does it take to update the finite element model?
It is not implemented so far. So
yeah, it is the last. It was the last slide, right?
Yes, it's the future work. It's on the civil engineering.
Because what we found very difficult is to you have your digital twin bridge. You can do simulation. You have results, so virtual results, and you have your measured data, and they don't match. So you are trying to tune your finite element model, but you have so many parameters in your model. So you don't know which one exactly you have to change to match with your measured data. Sometimes it's, I don't know, maybe it's abutment or maybe the, I don't know, friction in bearings or with your cable state or whatever. And you have so many different parameters possible, and you are like guessing, oh, maybe I will change these parameters. Oh, no, it's not what. So you don't, and you go back, and when you have like hundreds of parameters, I don't know how you will, do you have any, maybe AI algorithm?
For this orthotropic steel bridge, the finite element model was really good, so it was really accurate. It is a more current problem for the reinforced bridges. So there, the simulation of a reinforced concrete bridge is not so easy. That's where we came to this problem. You have already defined, so we are working on that.
Yeah, but for the reinforced, yes, you couldn't. I think what you said in the end, if I understood, it is too rigid to have the local deformation of each axle on the reinforced concrete bridge.
Sorry, so
the reinforced concrete bridge. Not steel, concrete.
Yes.
To understand that, what you said, the difficulty you have with the reinforced concrete in the end, this one here, it's because you don't have local deformation for each axle. It is too rigid.
Yes, yes. So
you can have maybe the total weight of the truck, but you can't have the precise distribution of each axle.
Yes, for the gross vehicle estimation, we have a solution, but we also want for axle load estimation. What is also a solution in those cases is the virtual simply supported beam method, when there are sensors installed in 3 cross sections. And for example, it can be calculated that from the so we measure at 3 cross sections, and from the cross section measured in the center, the signal of the other 2 cross sections are subtracted, and in this case we will have a virtual influence line and influence surface. And maybe it can be used in those cases. We also wanted to use it, but in this measurement, the 3rd cross section had some problem, and we have to re-measure things. So we have to reinstall that cross section, and then maybe we will have better results.
Yeah, very interesting. Maybe I should let the microphone to other people. The last one, just the last question, because we want to push this kind of study in France too, but we struggle with local and municipality and cities managing bridges. Basically saying we don't have money, we don't know technical stuff, and we don't know, and they think it's a good idea, but it's very difficult to convince them to invest a little money even for sensors. Sensors are very cheap now, but it's all the data, processing data, if you want to have a FEM model in parallel. So how do you convince?
The main thing is that here is the accelerated estimation is important because, for example, in the case, in the revenue of the state will increase if there is such a system.
For the fine, okay, because you fine them.
Yes, by fining.
Okay, that's a good point.
That's the.
Yeah, but I think actually in France we have an issue with that. It was blocked. It was blocked, and we had to do. It's illegal. We have to go to the parliament for this kind of thing because it's forbidden to fine a truck if we don't have some kind of police or you think like.
In the case
thing like that of you can't like a mayor can't fine or
in the case of Hungary you also have to be certified if you want to fine. It is not possible in this case yet, but it is also a big help if it works as a preliminary filtering place.
Okay.
So the police or the public roads can, for example, stop 30 vehicles in an hour. And if they know which vehicles should be stopped.
Yeah, you see at the end, after they cross the bridge, police can still say, oh, you go to the real balance somewhere to wait, a static one.
So they are at the end
it's a
of the
filter,
bridge at the stop position.
Okay, for big bridges, it makes sense. Yeah.
Yes, and they know which 30 vehicles should be stopped. And if 1,000 is crossing the bridge, then they don't know that these 30 should be, and they all be fine that this is revenue.
For big bridges, when you have spare, you can do that, yes. But for small bridges, you don't have enough balance, big balance for truck after each little bridges to control the weight, the real weight, with a balance. You know, a scale. I mean a scale, not a balance. A scale. Sorry, a big scale for truck.
For small bridges.
For small bridges, it's difficult to even for a police to ask to weight a truck. Actually, there is no easy way to officially measure the weight of a truck.
Yes. That's.
You need a big scale.
Yes. For example, in the case of this reinforced concrete bridge, it was a 30-meter long bridge.
Okay.
So now we are working on that. So this orthotropic steel bridge was about 500 or 600 meter long. This is 30 meter long, and it can be made more widespread.
Okay, thank you. Sorry, I'm taking too long.
No problem. Maybe you want to shorten the panel session, what you are managing. But, Attila is managing, coordinating the civil engineering part and both how to reach the municipalities, whatever, so we can discuss it with him. Do you have any questions from audience? I have two. What about this multiple lane problem? Do you think you can override it with using AI? Because if two trucks are in the next lane each to each other and they are traveling with a similar speed, how can you distinguish? So it seems very problematic.
That's where the deep learning was useful, because I commonly say that if we cannot solve it by human intelligence, then we will solve it by deep learning. And so if you can see that in the patterns, I can see with my human eye that what is the problem. And I learned that, for example, if I can label something with my eye, then possibly the deep learning will learn it as well.
Okay.
And yes, that's it.
About the scales, by the way, I don't know how it's going in France. We have huge scale stations, not only at the borders. No, not at all, and they're sparse. So how did you validate the results, by the way, in this case?
So in the case of the Komárom-Mosdori Bridge, we have 90 vehicles measured in stopped position by the public roads, and this was the validation dataset in that case. So. And the coast 323 standard defines how the classification can be done on such a data set.
Okay. Thank you very much. Yes? Use the mic, please. Thank you.
Hello. Thank you for your presentation. It was really interesting. Also the introduction to AI with the different fields and the little boxes that it includes. You mentioned that you produced synthetic data, approximately 100,000 scenarios, which is the ratio between the real data and the synthetic one? The ratio,
So have to validate it or?
No, the total volume of data that you used to train the neural network, you used real data and synthetic data, right?
Synthetic data. So
What's the ratio
yes,
between?
no real data. So no real
Ah,
data. Real data only used for validation.
Okay.
And that's so synthetic data was used only, and real data is only used for validation because it's really rare. So for example, if you can see that stopping 100 vehicles can take a lot of hours, and in this case we do not have so much real data, but if we would put it in next to the synthetic data set, then the deep learning would not learn anything from 30 data or 100 data, but maybe it would overfit on them. And that's why the real data is not used. So in fact, if the influence surface and the influence line is validated and okay, then the synthetic data set can be used.
Okay, thank you very much.
Thank you. Any other questions? If not, thank you again, Bence.
Thank you.
We will share the presentation with you if needed. Let's have a small break and we reorganize the room somehow, and we will have this panel discussion with our superstar alumni. Guys, let's start the last session, please. So András, Gyuri, please. So the lunch starts at 12:30. So we have quite a limited time. Pierre-Yves, you can sit over there if you want to hide your legs. Mic here, please. Yeah. Okay, so this is the last session with the alumni of Digital Twins. Let's meet previous or former students of the program. But we want to make it interactive. We want you to ask questions. We want to give feedback. If you didn't fill the surveys, at least respond to our questions. But please, yeah. Otherwise, you won't get this, the diploma. So, yeah. Okay. Okay. That's the last requirement. Okay. So let's start from the end. You already have your digital diploma. Gyuri, yeah, let's introduce them. So György Heus is from one key partner of BME from Czech. They are dealing project management and design in engineering. It's quite a big company in this area, like more than 300 co-workers. And Gyuri was in the first cohort, right? And András, András also the first cohort. And so Gyuri is an architect. András is a road engineer, and at that time he was working at another company, but now he is working also a road design company dealing with BIM and digitalization. And he's kind of an interesting mix because he graduated BSc in Austria, then MSc at BME, then finally canceled our specialized program and chose DigiTwin instead of BIM. And Pierre-Yves Lapa, and we are cooperating with Czech in multiple areas. András is member of our final exam committees in several of our programs because we really need such guy on the road engineering area. And Pierre-Yves Lapage from the second cohort. I think you all know them because he's a supervisor, and we also have connection with him because he's passionate about undersea photogrammetry. So it all started when they visited the Onsite event. He made a presentation to my department, and I'm from Department of Photogrammetry and Geoinformatics. And since then, Pierre-Yves is developing his own software doing photogrammetry. And now we are thinking about how can we integrate his research in our education. So I think it's a very nice cross transfer. And let me introduce Mathieu. Yeah. If you didn't meet him, the zero cohort, the boss. Yeah. Oh, the microphone. You need to use the microphone because this session is also broadcasted to the whole world.
And do we need to introduce Tamas?
Yeah, the housekeeper. So, yeah. So let's start from the end, and then we can go back to how do you feel about the education, what do you want to develop or whatever. But you have the diploma. Do you use it? Do you use the knowledge? Is it admitted? So does the industry value it? Or if not, how do you see in the near future? Who would start? Okay.
Okay. Well, how do I feel now? Quite well, thank you. If I use the diploma itself, no, because I didn't change my work. In fact, I kept the same job. Do I use the knowledge? Yes, of course. Just for an example, when I made my whole career in railway production, it means that I was able to manage train drivers, to supervise production of trains and so on and so on. And in a few years ago, I decided to join a new team dedicated of digital twin. the team is with 2 persons. Okay, it's a team. The 2 persons were in the court. Okay, Musa and I. And of course, we made a huge step from before to after, and we are now able to use our knowledge, and also to use the fact that we are able to acquire new knowledges, which is also important. And we are able to say to someone who want to show that he knows that we also know. Okay, so don't play with us. Sometimes it's important when you have to lead for projects. The problem sometimes is that digital twins is not a specialty, in my opinion. It's the fact that you're able to assemble several knowledge, many knowledge all together in a very special mix, kind of mix. And sometimes, well, some people think that we are able to do everything. For example, we are able to know how a bridge can react. The man just before that there is a kind of example like this one we have to deal with. So sometimes we have to say no, stop it. We are not able to do that. It's not our specialty. We are not able to build bridges. We are just able to inform you about what your bridge looks like. That's all. That's all. No more. So we have to build some barriers. You know. That's all. What is sometimes that is very pleasant, even if I don't answer, is I'm 56 years old, and normally, in my age, you don't receive any more job offers. I receive job offers. And I said, what a pleasure. And I said, no, thank you. Oh, what a pleasure. Yeah, it's a luxury to refuse.
Just one small feedback. We have, what you said, we have a master program for civil engineering background, people with civil engineering background, construction information technology. We teach Python, IoT, AI for these students. We don't expect them to be a programmer. We don't expect them to be an IoT specialist. We expect them to be able to negotiate, to communicate with IT guys, with professionals, and not be cheated, not be played. So they will be able to judge, think, okay, that needs two months of development. I can judge it. I'm not professional in programming, but I know the basics. So, and that's what I think in the construction industry, they are needing people like that.
Yeah. Completely.
Yeah. András.
What was the question? Sorry, I got lost in the story of peers. It was so good, really, I swear to you. No, sorry, just kidding. So, the original question was something like that, how can we use it? Do we use our diplomas? Of course, we were really part of the first cohort. I really think that we were before our time, and you are in the second cohort, still too early for it. But in a long-term thing, right now in Hungary, surely not. So I remember one time it happened that I read some news that the Hungarian roads are planning to make a digital twin section, and I was suddenly calling Tamás, hey, how is it possible that something like this will be made? And then it popped up that they don't really know that there are people like with this diploma, and there was a different kind of project, of course, and we didn't come into the topic that we can be part of it, even though I wish to be part of it, because I'm really interested about this digital twin part, plus it's on my working field, so it was really interesting. But in Hungary, we are far away from that point that we would be able to use this diploma. What Pierre also mentioned, the knowledge itself, it's great. Swear to you, I don't want to repeat you, and I make it pretty hard for Yuri because he has to say different things than what we said before without repeating anything. But really, you get a view where to go, how to develop something, how these things are connected to each other, and you have to adapt it to the field where you are right now working or where you are going to work. So really, it's this whole program, let's say it like this, gave me a completely different perspective because I was not so lucky, what Tamás also mentioned before, that they are teaching now for master, or in master, Python and all these kind of basics of IoTs, and I got these stones, basic stones in this program. So, Yuri, the mic is yours.
Thank you very much. You're really kind. Okay, so we like to start from the beginning. As an architect, among a lot of structural engineer, just like this. Okay. Okay, thank you. So as an architect, among a lot of structural engineers, but also colleagues, because in the company we have a structural design team also, and we are in a daily cooperation with them. It's no matter what kind of structure we design, it can be a building or a bridge, anything else. But it was very difficult to determine myself in the first cohort with the topic. But now I can see that the digital twin is a, let's say, a revolutionary new approach of the BIM. So 50 years ago, when the BIM came across in our profession, it was we walked in a child's shoes, let's say it, because there was no frameworks, no ISO, no regulation, nothing for the BIM. So it was very difficult to find our way in the market. But now, BIM is set as a default requirement, almost even in Hungary as well, and not only for an architect, but for everybody else as well. So I think that, and I believe that digital twin is the future, and another evolving step of the BIM design technology. With the very high support of AI. As we can see in the last 15 or 10 years, first the hardware is developed very quickly. Then now, currently, the software solution which supports the hardware develop very quickly. But for example, the industry, like a design or a construction, everything in the market is far in the backyard. So they need to develop and to adapt with the new technology and solution. But first, we need, of course, frameworks, right, such as ISO or anything else, which gives the good frameworks how to use the digital twin solution, not even in the design, but later in the facility management or anything else. So that's why I think, so the knowledge is very, very important now. We behave now currently like pioneers. So be proud of yourself, I think, and try to find your followers. Because we made a survey at the company and it turned out that a lot of younger colleagues are highly interested in, for example, Python programming. And Python is started to become a basic language for the parametric design or even for the automatization, not even in the factory or the production line, but in the design technology as well. So it's a very, very good and useful thing, but as András said earlier, if you would like to increase the scope of the usage of the digital twin, we are far, far away from the normal usage. It's a dream, now, but sooner or later it will be a requirement as well. And we need to meet the requirements. So we are engineers, we can solve this issue, I think. Thank you.
Thank you. Mathieu, do you want to?
Thank you. I don't know exactly, but just to maybe to continue on your topic, you're here about the BIM. I don't know. You said now it's mandatory in Hungary, and so in France it's not yet mandatory BIM. Sometimes yet, sometimes not, but it's not a national regulation. And the thing is, from my point of view at École des Ponts, we have also a master in BIM, dedicated only to BIM. And we have seen, like after 10 to 15 years, that there are like a decrease in interest in BIM, even in companies in France, because it was such a big move at the start, a big wave in 10 years ago. A lot of companies spent money to equip, to train people, to buy software, and to start to develop a lot of projects with BIM. But actually, in the end, they got lost, and they thought it would be a dream tool, but in the end, they were quite a bit disappointed by the BIM. And so this is we have this curve, we say, of BIM, and now there is kind of a normal balancing. We were like in a transient state for the BIM acquisition, and now I think with the time we have a normal usage of BIM, and people take time before doing BIM, and they don't jump directly to BIM because it could be expensive, especially for small companies. They don't have many budget to buy everything, to train people. And that's the link with digital twin, because when we speak, and it is for everyone, like for us, when we want to foster digital twin, I struggle a lot sometimes with people telling me, "Oh, this is the new name for BIM. I know it's a dream tool. No, I don't believe in that. I want practical thing. I don't want this dreamy thing." So it is our job also to, when we foster digital twin, to not sell only dreams, but to have a practical approach. And even if it's link what you said about regulation in ISO, because we don't have, and we can ask Marcos about definition of digital twin. Each company has its own definition, so when you discuss with them, sometimes it's so we are in a position, a difficult position, to explain, to make it simple, what is our vision of digital twin, and how we can be useful and practical, concrete approach, without selling or overselling this kind of new tools. So it's not, and we are all, basically all architects or engineers, and maybe we are not very skilled in communication and this kind of thing. So this is also difficult for our cohort, not only the students. I mean, even myself, when I discuss, I have a technical approach, and so it's not so easy to convince people like that. I don't know if you share the same feeling, Tamas.
Yes, I do, but we don't have time for my speech.
Oh, yeah, but come on, it's too easy.
No, I feel, we were smiling with András in the meantime because we are mentioning the Hungarian BIM regulations, which is basically saying you need to use BIM, but it doesn't specify how to use it. So you used to do CD, but how to use it. So if I submit, I don't know, a 3D drawing, and that's BIM because it is coming from Revit, then they will. But we are, at least we are working. So I think as a first step, that's okay. That is kind of okay. You can talk afterwards.
I'm not here to judge the Hungarian BIM system and regulation, but yes, it's great like a first step, but the following steps are missing.
Yeah.
Let's say it like this.
Yeah, but as a university, I believe in knowledge. I believe that if we train the future generations for that, they will know, okay, that's not okay now, so we need to proceed another way, so that's fine. And I totally agree with you. We experienced the same with BIM in 10 years ago. We were catching students in BIM, and now I'm overbooked in all my BIM trainings because they realized. And because the job market say, okay, if you have a BIM diploma in you BIM specialist, I give you more money. Or even, I don't know, what is közbeszerzés in English? So when they have national projects, and they are competing, and they have a requirement, BIM certificate or equivalent, and our BIM special program says, okay, if you're not it. So that's why they need, that's only also a drawback, because students are now coming from paper and not for knowledge, because they start, okay, this paper have this value on the market. And I really enjoy the first cohorts in my BIM programs, because at that cohorts, the students were just for knowledge. And now companies are standing, I need that paper, go. And the student, okay, I don't want to study that one. So it's pretty challenging to us, but that's what we need to do.
Public procurement.
Okay, public procurement. I love this. Okay, enough about the big picture. Let's go and see what about, we try to remember to the program. And Gyuri and András was the first cohort, and believe me, it was even more struggling at that time, because they had 4 days a week, 3 hours in 4 days, not 2, even Thursday, and much more. And the program was much more fragmented. They met 70 professors during the program, so they were struggling. And András has other problems, switching workplaces, having a baby, so he enjoys challenges.
Business as usual, so. Sure.
He thought it was too boring. So, if remembering back, what do you think was the most struggling generally about the program? And I want your feedback also. And also you can mention some struggling subjects, courses. Oh, that was really challenging for you, because I didn't have any background and the speed was too fast. So let's be honest now and talk about that. Who starts?
Okay, I have.
Oh yeah. Okay. They are already in the system, so.
So then I would start.
Yeah.
If I allowed. I'm telling you completely honest. We were first, so we also realized that this is the first edition. So also from the other side, you didn't really know how it can work with people who are having a decent job, and not just students who have endless time and endless nights. So actually, the time was the biggest problem for us. The load was pretty big at the beginning, and as I heard for you, it's much easier right now. Compared to, let's say it like compared to our load, but I don't know how it works for you, but you have to judge it. Yeah, the time was for us the biggest problem, because you are working a decent job, you work until 4:35, depend on which time zone you are, because we had a colleague of ours who was in Turkey. For him, everything was a completely mess, depending on the summer or winter time. And then I remember some of the subject I was already listening on the public transport while I was getting home, and then I was continuing it until 8, usually by the night. So that was a whole day. I wouldn't say the word struggling, but I don't know any other which would describe it perfectly. But it was not struggling, it was a big load, let's say it like this. And if we are speaking about the subjects, I speak again about the first cohort. There were some, I think it was expected from us a bit more what we actually had. I mean, for basic of programming and these kind of things, because we were the first cohort. So I really think that there was no picture in front of us what this whole, we were interested. I think we were the first, we were the people who were like, hell yeah, I need it. And I have no idea what is it exactly, but I know I need it. So we had our extra motivation for it. And many times we also faced it that, for example, I remember at the end in the capstone project we had machine learning, but at the very beginning of the cohort or program, sorry, I also learned what was written to machine learning. I was like, it's too much for me. But during we were doing the capstone, and the colleague who was participating in the machine learning class, I was like, bad luck, I didn't. I supposed to be part of it because it was so interesting, and who was educating it, that was a great guy, and he explained everything so easy. Same for IoTs. So the only struggling with it was like we didn't have a real picture yet of course, you, thanks God, you have it. Which subjects we supposed to take that it fits for us the best. Yuri, Pierre?
Okay, thank you. First of all, I don't prefer this struggling expression, so I would like to use the demanding instead of it, okay? Not just because the difference, but the most demanding things in the first cohort was when how to join the program even, because I graduated in 2005, so a lot of my papers haven't been translated into English yet. So first I need to do a translated job, and after it I was able to sign for the program as a first cohort member. So from here I would like to thank you, all of your teacher team and everybody else who was very flexible and helpful to me to make it possible to join to the program. So thank you very much again. And so I was able to join 2 weeks later that the program was started. I remember now. Just to remember it, okay?
Struggling to us.
Yeah, so for evening, according from 5 p.m. to 8 p.m. CET, for evening, I would stay in the office and listening with the courses, and then during the weekend, I try to watch the recordings. Because and then I started to do the homework. Because there was homework, there was a lot of yes, tasks to finalize. So the first semester was very demanding and exhausting for me, but I was able to manage in the very end. I don't know how, please don't ask it, but I was able to manage it. I finished my tasks and homeworks, everything, and I was really delighted and delightful when I arrived to Madrid to the first workshop. It was, how to say, more than I expected, much more than I expected. That was the first time I met my classmates, colleagues, foreign colleagues, everybody else. The first time we were able to meet, to speak to each other. But the second semester was much more demanding because Python coding came across and we were unable to talk about, for example, the machine learning. It was a very, very difficult and full of mathematics subject, so it was hard to understand, but I'm really respectful because now I can read the Python program code, almost everything. I know where to search, where is the sources, almost everything, and I'm still learning Python coding because my company supports this. So in the custom project, it was another thing. It was really hard to understand what they want from me. But yes, I can remember I needed some time to clear in my mind the goals, the task, and with my help of my classmates, we were successful in the very end in Paris. It was beautiful. Thank you.
Let's wait for Pierre-Yves' answer, and then we can hand over to the audience. Okay?
Yes. No. It's okay. Never mind. My main problem was that I began those courses. I was 55 years old. I've only been in school from 25, from 55. So 30 years without school. And then you go back to school and